So we talked about derivatives of logarithmic functions. Today we're going to use logarithms to make differentiating some functions easier, even if the original doesn't have a logarithm in it. But to start with the warm-up, if you look at this one, it's just a nice regular power function, except our exponent's square root 2. So my derivative is going to be square root 2 times x raised to the square root 2 minus 1 power. Other things that we've done have been some exponential functions. So say that you have like g of x equals 2 to the x power, and your base is a number and your exponent's your variable. You know how to find the derivative of those. So what we haven't done is, what if we have sort of a combo where the base of my function's a variable and so is the exponent? That's what we're going to look at today. They are going to require a process called logarithmic differentiation. So how logarithmic differentiation is going to go is basically we're going to start by taking the natural log of both sides of our equation. So we're not doing any derivatives to start with. We're just taking natural log of both sides, and then we're going to simplify our equation using properties of logarithms. Then once we've rewritten it, we're going to use implicit differentiation, and eventually we're going to solve for dy dx and rewrite our final answer in terms of just one variable, not two, if possible. Which I know sounds like, the absolute most simple process in the world. So let's do one. It's actually not horrible. I'm going to rewrite this just with y equals instead of with my function notation. And then I am going to go ahead and take natural log of both sides, because that's going to allow me to rewrite it in the form that I actually can find the derivative of using what you already know. So taking natural log of both sides, and then on the right hand side I can use properties of logarithms to expand that, because I have things being multiplied together inside my log. So let's expand it out into the two logarithms being added. And then I can go ahead and rewrite that second part as x times natural log of x. Now I haven't taken any derivatives yet. I've just rewritten it. So now it's time to take the derivative. So if I take my derivative, I'm going to have 1 over the inside of my logarithm times natural log of my base, which is e, and then chain rule times the derivative of the inside of my log, which is dy dx. And then on the right hand side, the derivative of natural log of 2 is just 0, because that's a constant. The second part I'm going to have to use product rule on. So I'll have x times the derivative of natural log of x, which is just going to end up being 1 over x, plus derivative of x is 1, times natural log of x. Simplifying here a little bit, on the left I have 1 over y times dy dx equals, if I multiply things together, I just get 1 plus natural log of x. Now I'm finding my derivative, so I need to solve for dy dx. I'm going to multiply both sides by y to solve for that. And then I'm going to have y times 1 plus natural log of x. I don't really want this written with two variables, so let's go back up. Y was 2x to the x power, so I'm just going to replace that back so that it's written in terms of x, and there's my derivative. Okay, so if you're working on this derivative, the first thing you're going to want to do is, I'm just going to go ahead and write it as y equals instead of g of w equals. And then that would be horrible to take the derivative of as it is, so I'm going to do natural log of both sides to make it easier, which means that you can just expand things out and have something that is way easier to take your derivative of. So if you expand it, everything that was being multiplied together on top there, I can turn it into separate logarithms being added and bring my exponents out in front. And then my denominator, I'll have that logarithm being subtracted. And don't forget my 2. Then it is ready for you to take the derivative of. So we haven't done any derivatives yet, but we're about to, because now it's in an easier form to do that of. So if I do the derivative of both sides, going to have to use a little implicit differentiation. And then derivative of natural log is just 1 over x, 1/2 times 1 over my inside of my logarithm, minus 2 times 1 over the inside of my logarithm. And don't forget chain rule, multiplied by the derivative of the inside, which is 3. Okay, I'm just going to simplify a little bit here before I start solving for dy dx. So I'm going to multiply my last values together and just make that into a 6 on top. And then I am solving for dy dx, so I'm going to multiply both sides by y to get that by itself, which is just going to give me y times everything that I had right up above, so yay for copy and paste. And then I don't really want to leave it written with both y's and x's in it. Let's get it to one variable by going up and looking what y was originally. So if I replace y with what it is in terms of x, it's not going to be a very pretty derivative. I could possibly simplify, get a common denominator, but I'm going to leave it like that. Ta-da! So now we're going to write an equation for the line tangent to this graph at the point 2, -4, which means we get to take the derivative. So I'm going to use logarithms to make this easier to take the derivative of by doing log of both sides of my equation, and then I'll expand it out, which, if I expand the right-hand side, it's going to be natural log of x plus 1/2 natural log of x plus 2 minus natural log of 1 minus x. And then it's ready to do my derivative of. So if you take a derivative, I'll have 1 over y times the derivative of y with respect to x equals 1 over x plus 1/2 times 1 over x plus 2 minus 1 over 1 minus x, and don't forget the derivative of that inside would be -1. And then I'm just going to go ahead and multiply my two negatives together and make that last one into an addition instead of a subtraction. And then to solve for my derivative, I'm going to multiply both sides by y and copy and paste. And now if you look at what we're doing, we're supposed to write an equation for our tangent line. So really there's no point to replacing y with our original value for y. I'm just going to go ahead and plug in my y coordinate of -4 and my x value of 2 and see what slope it is that I get. So if I plug those values in and then simplify a little bit, I'm going to have -4 times 1/2 plus 1/8 plus -1, which if you simplify is going to give me 3 over 2. So my slope of my tangent line is 3/2 at the point 2, -4. So if I write my equation, y equals mx plus b, I can plug in my x and y values and then solve to get my y-intercept, which is going to end up being -7. And then I've got my equation of my tangent line is just y equals 3/2 x minus 7.